All right, let's go through another example. This is from your readings from this week, so you may recognize the data set that I have included in here. And so this is a hypothetical data. All right, here's another example. This is a life table. And this is from your readings this week, so the data may look familiar. And this is a Kaplan-Meier life table estimates for survival after heart transplant. This is hypothetical data that I pulled from your textbook. So what you see with a life table, you have month of death here, the total number of patients at the beginning, and you see because as people are having the event, in this case, death, the event is of interest is death, the number goes down by 28 months. We started with 74, we went to 42. This is the number of deaths that occurred in this month. This is the probability of death, which is simply D divided by P. The probability of survival is essentially 1 minus D divided by the total number of patients. And then you have cumulative survival. So at the beginning, what we see here is we had 10 patients die. So the probability was we had a 13% death rate at that point. So the probability of survival is you just take that and subtract that from 1. And so we had approximately 86.5% cumulative survival at that point. Then here we go down to month 3. We had 4 patients who died. So the number, we've had 14 total, so we've gone down. So you have the probability of death at that month and the probability of survival. So then what you do is you have 0.809, which is taking this number multiplied by this number. You can see as we go on and on like that. So you have 1, 1, survival. So then say, what is, example, if we get the probability of surviving at 15 months, how do we calculate that? So you take the probability of surviving at 12 months times, or multiplied by, the probability of surviving the next 3 months. So what we have right here is 0.742. Remember, and we're saying the next 3 months is basically from that last time point that we measured the occurrence of the event. So basically what you're doing is you're multiplying, taking 0.742 times 0.96, and this is how we come up with 0.712, or 71. Or the cumulative survival at 15 months was 71%. And that's what you can see right here. If we were to imagine an imaginary line right here, that's probably about, it would be about, I say, 71%. So you can see here, we had those 10 patients die, then we went a few months, 4 patients die, you kind of go down and down and down. It was a very flat line after that point. Here's some from your readings this week as another example of showing, these are children and adolescents with essentially brain tumors and metastasis. And what they're showing is sometimes you'll see in especially cancer literature is they may talk about a 10-year survival rate. So, and what they're saying here is the median survival could not be determined from this particular data. So maybe they were using a 10-year survival. So they were saying it's 70% as compared to 36% in this group here. And they were able to calculate the median survival as 2.9 years. This is from this particular study. Now, what you can then do is how do you compare differences between the groups on survival time rates? Well, this is where you use a log rank test. So it's a non-parametric test. So it's distribution free. To use to test for survival differences between the groups. The null hypothesis is that the ratio of the hazard rates in the two groups is equal to 1. So if we look over here in this figure, this is time from primary surgery to death in years. Here's our probability from 1 or 100% down to 0. You can see here there's a number of, in the maintenance chemotherapy group, it looks like, just looking at it graphically, they have better overall survival. I mean, at 10 years right here, that is 70%. Whereas here, at 10 years, it's 36%. All of these are censored events. Maybe they were lost to follow-up. They would have to need, in the manuscript, they would need to be a little more specific with what those events were. Here's the other figure we looked at earlier. Remember, these are median survival times between these two groups. Now here we're looking at, they've done the log rank test. So what we see here is we have radiotherapy, and we have radiotherapy plus a chemotherapy combination treatment. So here we had a number of patients who had relapse with 70, and this was 54. That was time to, may have been the event that they were interested in. The median survival we see here, 0.64, 1.1. And then it has some expected numbers, so it's it's expected based on the statistical calculation. So what it does is really the bottom line is it comes with a hazard ratio of 0.58 and with a rate of 0.41 to 0.83. Now what does that mean? And now that was statistically significant. Even if I didn't have that p-value, I know that's statistically significant because it does not include 1 in the confidence interval or in that precision measure. So what does that mean? Well, what you can do is you can say, if you take 1 minus 0.58, you get 0.42 or 42%. So there was a 42% lower risk of relapse in the combination treatment group. So that's how you can determine the magnitude of an effect with the hazard ratio. If this was 1.58, you would simply subtract 1.58 from 1, and you could get the same thing. All right, here's another example. This was the study that we did with our students looking at time to complete motor recovery. Just looking at it, I would say there's not much difference graphically. I mean, there's a trend maybe that the saline group recovered a little bit faster, but they're pretty darn close to each other. Now, in this case, we did not have any censoring of data, so ignore these tick marks on here. So the hazard rate ratio was 1.3, and the confidence interval, the measure of precision, was 0.65 to 2.6, so a fairly large confidence interval. More importantly, it includes 1, so it's not statistically significant, and we can see that reported right here. What does that mean? Well, even though it's not statistically significant, what it does show is that the control group had a 30% longer time to full motor recovery when compared to the saline bolus group. However, it was not statistically significant, so we concluded there was no difference between the groups in time to full motor recovery. And time to full motor recovery was the dependent variable or the event of interest in this particular study. You can see what we've done over here. Instead of using the ratio, we just used the percent, which you'll sometimes see. I think this is sometimes a little bit easier to comprehend when you're looking at it. We could have also easily have reported the median time to survival or the median time to complete motor recovery with this, but we we decided not to in this particular group. Here's another example from anesthesiology in 2009, where they compared early versus, like early latent labor, like before the patient even was actively in active phase labor, say a CSE at 1 centimeter versus a CSE at 4 centimeters. And this was a rather large trial where I think they had close to 10,000 participants, and it was done in China, I think over about a 5-year period. So one of the things you can look at, so this same thing, they use percentage rate here, time to the event, time, and they represent that within minutes. Here they're showing you'll sometimes see these in survival analysis. Here they're showing the number of at risk. So here we started with 4,800. We'll keep going, then it starts going. The rates are changing over time as people are experiencing the event of interest, which is time to vaginal delivery. So these rates will continue to drop down. And so they're able to model, diagram out this data set here. The other thing that it shows you is they do report the median time. So the median time in latent phase labor was 627 minutes as compared to 661 minutes. Now, they didn't do a log rank test. They just compared the differences between the groups in median time to delivery. And it was only about 34 minutes difference shorter in the latent phase group. And they showed here, if we look at that, it's not statistically significant by looking at that p-value right there.